What's up, fam squad? Chucky Hats out here, and welcome back to my Minecraft Let's Play episode 6. In yesterday's episode, we finally faced our fears and went to the nether to get 10 beautiful ender eyes. And now we can put them in the ender portal to beat the final boss of Minecraft. So, without further ado, let's suit up. And we'll get going. We'll get going. So true Minecraft experts know that you always have to put the ender eyes in the ender portal before you go to the end. So let's hop right in. Let's hop right in. Gotta be ready to fight the dragon. Gotta have my sword out. To defeat the ender dragon, you must answer this one question. What is a derivative? Okay. Well, the understanding of a derivative is all underpinned by the understanding of rate of change. Slope-intercept form is y equals mx plus b for a linear function, where m is the slope of that function. That is the average amount the function increases in y per increase in x. Therefore, it can be found by dividing the change in y over the change in x. Finding the slope of a linear function is simple because it is constant. As can be seen in the table of f of x equals 2x plus 1, the y changes by 2 every time x increases by 1. This is corroborated by the graph. The instantaneous rate of change describes the rate of change at an exact x value. This can be thought of somewhat as the speed of the graph and how it's changing at that exact point. This is simple to find in a linear function because the slope is constant, and in that case, it is always 2. However, finding the instantaneous rate of change in a curve is much more difficult. Take, for example, x squared. There is no constant rate of change, and this makes determining the instantaneous rate of change very difficult. However, the instantaneous rate of change can still be found, or at least approximated, because of local linearity. As can be seen in the graph of x squared, it begins to look very curvy. However, the further you zoom in, it begins to more and more resemble a line. Local linearity is predicated on the assumption that if you zoom in far enough, any curve will look like a line. The instantaneous rate of change, therefore, will be the slope of this locally linear segment. The slope of this line will be the same as the line tangent to it, meaning the line that passes through exactly that one point on the function. Take, for example, x equals 1 when f of x equals x squared. The tangent line in this case is 2x minus 1, as can be seen in the graph. When we zoom in on the point 1, 1, being the place the two lines intersect, they are virtually indistinguishable. Finding the slope of the tangent line is the same process as finding the slope of any linear function, and that is to divide the change in y over the change in x. This is stated through the difference quotient. The difference quotient is that the f of x equals x plus delta x minus f of x all over delta x. So let's apply this, for example, to x squared at point equals x1, at point x equals 1. Using the difference quotient with the delta x of 1, it can be seen that the slope of the tangent to the slope of the line tangent to x equals 1 is 3. This clearly conflicts with the 2x minus 1 tangent line we've already identified. What we just made there is a secant line, but not quite a tangent line. The difference between a secant line and a tangent line is that a secant line passes through 2 points along the function. This is the way that a difference quotient must work because it needs 2 points to find the change in y. However, local linearity saves us again. Linear functions don't have this problem because their slopes are constant. So, if we apply the difference quotient to the very zoomed in area of the function, it should work just as well. Changing delta x to instead 0.0001, it can be seen that the difference quotient yields a number that is approximately 2. Well, you may not have realized it. What we did there is approximate the derivative of f of 1 when f of x equals x squared. The symbol f prime of x means that the derivative of the function f of x, and that is just how we talk in calculus. This process can now be applied to any individual input on the graph. However, it would take forever if I wanted the instantaneous rate of change for every point in between negative 100 and positive 100. Luckily, we can apply the difference quotient to the function as a whole. This blue line is the difference quotient being applied to the f of x equals x squared. This follows the line of 2x almost exactly, meaning that we can say the derivative of x squared is 2x. Thus far, we have been approximating the derivative. However, we have not yet been able to conclusively prove these derivatives. To do this, we would need to set a delta x that is 0. This, as can be seen, is impossible because we cannot divide by 0. Instead, we use what is called a limit. A limit defines some variable as infinitely approaching a given constant. The answer to an equation including a limit is what value the limit seems to be approaching at that point. This is useful, for example, in the function y equals x times x plus 1 over x plus 1. We cannot solve for x equals negative 1 because this would make the denominator 0. Adding a limit to this expression would allow us to simplify it. Algebraically, the x plus 1 in the numerator and the denominator cancel each other out. So as x approaches negative 1, y will be negative 1. We can now apply this concept to the difference quotient. Because delta x infinitely approaches 0 in this way, the equation will give an exact value for the derivative. This is called the limit definition of the derivative. Note that I replaced delta x with the letter h. In this case, they both mean the same thing. H is just more commonly used and is simpler to write. So we've already established that the derivative of x squared is probably 2x, but through the limit definition, we can prove this. By plugging in the values and simplifying the equation, it eventually reaches a point where we cannot simplify any further in the numerator. However, all terms in the numerator now share a common factor of h, meaning that we can factor it out. The numerator and the denominator both have h in it, meaning that those two cancel out. So the new equation just becomes the limit as h approaches 0 of 2x plus h. And now we don't have any problems dividing by 0, so we can plug in 0 for h because of our limit sign and find that the f prime of x equals 2x. This can be applied to even more complicated examples. For example, the derivative of 2 to the x. Because the x is in the exponent, we have to add delta x to that exponent as well. So the first step in this is, because of exponent rules, we can say that 2 raised to the x plus h equals 2 to the x times 2 to the h. Now, both terms in the numerator share a greatest common factor of 2 to the x, therefore we can factor that out. So there's a rule in math that as a constant raised to a variable minus 1 over that variable, as that variable approaches 0, the answer to that expression will approach the natural log of the constant. So applying this now to our derivative, we can see that 2x, or 2 to the h minus 1 over h will approach the natural log of 2. Therefore, the f prime of x equals 2x times the natural log of 2. Oh my gosh, you have successfully explained the derivative and also beat the Ender Dragon. And now we get a cookie. How fun, yay, we did it. That's calculus, baby. That's derivative. Goodbye.